This is an overview of a project started maybe 6 months to a year back. In its current configuration, it's a CW transceiver with 100 watts out, primarily used for rag chewing on 80, 40, and 30 meters. In implementing this project, I had two major objectives. One, to maximize the performance per dollar spent, and two, minimize the effort needed to build it. I also had a third objective, and that was to do it in such a way that it could be replicated. Now, to be clear, this is not a kit, and my support for it is limited. But because I use what I call a Lego build style, and it's built around parts mostly available through eBay, I believe if you have a computer that can run Linux Mint, then it should be possible to assemble this rig for $150 or less. And because of the Lego build method, I'll add you won't have to spend $150 before you can start having fun with it and turn it on. So, to better understand what I'm talking about, let's start by taking a look at this board. Basically, I think of it as the heart of the project. What is it? It's the electronics for a Tayloe mixer type receiver using an SI5351 VFO and an Arduino SS Micro for control. Basically, it very closely follows the SoftRock receiver design. Now here's the bad news. You'll have to make this board yourself. But note, it's a single-sided circuit board and uses through-hole construction. I estimate that if you build it, the parts should set you back less than $20. Again, with through-hole components and a single-sided board, it should be quite buildable. If interested, you can follow the link in the intro to this video to the GitHub site where the Eagle files and the Arduino sketch plus other related files unique to this project can be downloaded. Now, let's look at how this board integrates into the project. I'm using a piece of open source software originally developed by Jim Ostrom into ADR called QUISK. It's written in Python, and for this project has some minor modifications, primarily to make it compatible with the Arduino sketch and to augment how it interfaces with FLDIGI. Also, another open source application and written by David Fries, W1HKJ in C++. And like QUISK, it too has been modified for this application. Both have been around for a number of years and have way too many neat features for me to do them justice here. So let me state the obvious. The board paired with these two pieces of software really makes it possible to assemble a station at virtually no cost. And without the hard work of these folks and many others, this project would not be possible. All I've done here is bundle them up into a compatible package. Speaking of bundling and home brewing, many folks today say they can't home brew because the parts are too small. In my opinion, the real showstopper for many a homebrew project is boxing it, which means adding knobs, meters, switches, and lights needed to operate it. But here, the software sidesteps these complications, making that aspect of the project a breeze to get up and going. QUISK, working through an external sound card, harnesses the power of the computer and makes this simple VFO mixer board do things that a few years back were only dreamt of. The most obvious of these is having a near real-time view of practically 100 kilohertz of spectrum, thus making it easy to find and assess activity on the band you're listening to. For CW work, QUISK offers the user a number of filter settings down to as narrow as 200 Hz. Its receiver incremental tuning is handy for working with a station that has drift issues, and QUISK supports split operation too. There's a noise blanker, which can be helpful when you're troubled by local line noise, and with this modified version, there's a 0 beat button, which literally makes it a snap to set your transmitting frequency to that of the station you're listening to. Using pulse audio that comes with Linux Mint, it's easy to route the audio output of one application into the input of a second. In this project, the output of QUISK is piped to FLDIGI. Additionally, in the background, these two applications are asynchronously linked such that one knows what the other is doing. Now here's where this project may get controversial for some, but for others will open a door to a world of conversation that have previously just been noise. FLDIGI sports a good CW decoder. And being a lazy engineer with no short-term memory, this decoder is a nice accessory. If you're new to CW, use this feature to spend some time reading the mail on other QSOs. You'll quickly find that spelling is optional, and there are many shortcuts used to speed up the conversation. For example, TT will often be substituted for the word that, and in other cases, TT will replace the zeros needed to specify how many hundreds of watts being used. There are too many to review here, but most will be obvious when seen in context with what's being said. Next, let's look at the transmit side of this project. Here, because of the Lego build style, you can configure the PA unit to be whatever suits your needs. For those who want to operate QRPP, here's a 100 milliwatt PA that I built, and if interested, the GitHub site contains Eagle files for this unit. Also at this point, to facilitate switching from transmit to receive, I built this little board using a 5-volt relay. Now, to be honest, this relay was the one part in the project that was given to me. So for this part you'll be on your own, but it has a common form factor and would think that it wouldn't be that hard to find an equivalent. As a transmitter, this is the simplest iteration of this project and, as you might expect, is also the cheapest to get on the air. The downside of this little rig is band changing. It's a manual affair requiring you to swap both the transmit and receive filter assemblies. But on the upside, it's all powered from the computer's 5-volt USB port, so no external power is needed. For most of you, probably the biggest negative is its 100 milliwatt output. But be assured, on CW, with patience, you can make contacts with it. My best contact, distance-wise, was approximately 450 miles on 40 meters. Both thrilling and scary to think that this little amount of power escaping from your rig can clearly be detected 450 miles away. The strategy I used to make contacts with this PA was pretty simple. Listen for a strong 5-watt QRP signal and then go back to it. Like all QRP QSOs, it's really the receiving end that's doing the heavy lifting. But on CW, one can give their transmitted signal a big boost by having a good fist, and that's where FLDIGI makes this rig a strong performer. A receiving station will be much more attentive when your code is sent with precision. Thanks to FLDIGI's built-in keyboard encoder, the cadence of your sent signal will come across like that of W1AW. Now that was into a dummy load. Let's watch as we put this 100 milliwatt transmitter on a 40 meter inverted V, send a test signal, and then use the reverse beacon network to see who hears us. Okay, two stations heard that. One was N7TR. Google Earth indicates that N7TR is roughly 1,900 miles away. Dick Hallman, N7TR, I thank you for helping to demonstrate what's possible with just a little power and a clean fist on this end, and clearly some great equipment on the receiving end. Now, for those who want to get a little more power out but still retain QRP status, here's a way to move up the power scale to something on the order of 2 watts. And because the ultimate goal of this project was to get somewhere close to 100 watts out, this is a good point to implement a number of changes. Again, using the Lego style, these changes are relatively painless. Also, in the spirit of keeping the project reproducible, I sacrificed some economy and bought this pre-assembled broadband amplifier for just under $18. Now, this PA is a 12-volt unit, so the project needs a 12-volt supply. You can build these from scratch, but on the other hand, a 12-volt 10-amp supply like this one only costs $11 and will work on the 100-watt version too. So that's the route taken here. Another module needed to make this rig more user-friendly is a switch set of low-pass filters. An eBay search returned this board. It can be bought in kit form for $39 or pre-assembled $47.50. The lazy engineer in me went the pre-assembled route. Now, to tie these modules to the base receiver control board, I built these 2 daughter boards. One is essentially a solid-state switch which allows the push-to-talk QSK command sent to the Arduino to key the 12 volts applied to the PA. And the other board, using a BCD to 10 decoder IC, operates the low-pass filter relays based on the transmit frequency commands sent to the Arduino. Like the other homemade boards, these are designed around through-hole components and are single-sided boards. So while my boards were made using a CNC machine, hand-wired equivalents could probably be made just as fast and work equally well. The GitHub site has Eagle files for these boards too. So, using the parts just described, here's a demo of our 2-watt transceiver working into a dummy load. Now, to get something like 100 watts, I bought this eBay amp. Like the low-pass filter assembly, this amp can be bought either pre-assembled or as a DIY kit. Because I wanted to use a modified version of it, I elected to go the kit route. The downside of going this way is you also have to come up with a heat sink. But heat sinks aren't that expensive, and drilling and tapping it was doable with the tools I already had. Now, when you start plugging one power amp into another, things can get tricky. Basically, it's a Goldilocks problem. Too little power in will yield not enough power out, while too much power in will melt your finals. To be honest, it took a couple of tries to find the right balance. And here's what worked for me. I changed the finals drain to gate feedback resistors from 100 to 200 ohms. I added a 300 picofarad drain to drain capacitor and placed 2 4.7 910 picofarad RC networks in parallel with the primaries of the output transformer. Then on the RF input side of the amp, I wound that transformer with 4 turns on its primary. Additionally, I also modified the pre-assembled 2-watt PA by replacing its 2 inductors with 220 microhenry units. And finally, I added a 680 ohm 0.1 microfarad negative feedback network to the output stage. These changes were done to flatten and extend the low frequency response of this 2-watt module. Happily, they yielded a setup that reliably pumps out very close to 100 watts on 40 meters and somewhat less than that on 30 and 80 meters. Now, to be clear, to achieve this kind of performance, the antenna must look very much like 50 ohms. And we're talking about an output duty cycle that doesn't go much north of 50%. Another way to say it is, it works well, but by no means is bulletproof. My antennas are a fan V for 40, 30, and 20 meters, and a simple inverted V for 80 meters. So, in my case, the amp never sees anything less than 50 ohms. The rig has completed literally hundreds of rack-chew type QSOs with sustained 4 to 5 minute transmissions without mishap, but will not last long working in the loads much under 50 ohms. Now, if you happen to exceed the amp's limits, the good news is the IRF 530s are easy to change and can be had for as little as 50 cents each. That covers the core hardware. So now let's take a quick look at some additional parts that I think of not as necessarily essential, but as embellishments that are well worth their cost. First is this voltmeter amp-meter module. The way I have it wired, it shows what the 12 volt 10 amp switching supply is doing. With it, you can quickly learn what normal idle load looks like and what are normal key down currents. The next piece to look at is this little OLED power monitor. It gives a quick report of what the final PA is doing RF-wise. One point to note is, while I call it a power meter, because its display reads in dBm, it's really a voltmeter, and its accuracy depends on the load impedance that the amp is driving. So will only read true when the load on the PA is 50 ohms. In this setup, I have it connected to the antenna lead via a homemade attenuator. And while in the real world the actual reading may be off a bit, I find it gives repeatable results, and combined with the key down current is a good transmit health check. Next piece that I want to present is this boost converter. It's connected to the output of the 12 volt supply and is the DC source for the 100 watt PA. With it, the voltage applied to the finals can be stepped up or down, allowing you to tease a few extra watts out of the PA, or dial it back a bit if it looks like it's being overloaded. And finally, to support the converter, I've added another small voltmeter module that continuously monitors its output. The last item to cover here is probably should have been reviewed when I first introduced the baseboard and was describing the receiver. When I first built the receiver board, I scratch built a series of filters for it. But now I'm using bandpass filter kits from QRP Labs. They sell for $4.50 each, take about an hour to assemble, and have 50 ohm input-output impedance. So in my opinion, are a great fit to the goals and spirit of this project. Currently, I'm content to manually swap these filters as I go from band to band. But QRP Labs also sells a motherboard that will host a whole set of these filters, and in theory could be integrated into this project in the same way that the transmitter low-pass filter assembly has been. Now, earlier I said that the software had too many features to review. But I do want to take a moment and explain one feature of it that's peculiar to this project, and that's how FLDIGI keys the transmitter. Normally, FLDIGI uses the computer sound card to generate an audible tone, say 750 Hertz. The sound card speaker output would traditionally be connected to a single sideband transmitter's audio input, where the frequency and volume of this tone would then set the transmitter's final frequency and power output, much like what happens when you whistle into the microphone. Here, in this project, the sound card still generates a tone, but other than driving the computer speaker or a pair of headphones, the tone does nothing. Instead, concurrent with the tone being generated, this project's version of FLDIGI sends via QUISK a data stream indicating key status and duration to the Arduino's USB serial port. The Arduino then translates this into data that turns the SI5351's clock 2 on and off as needed to replicate the dits, dots, and spaces to send your code. Like most digital streams, this stream is buffered and flows asynchronously from FLDIGI to the Arduino. So, while most of the time the RF output appears to be in sync with the sound card's tone, there can be moments where there's significant latency between the two. So, this rig does not claim to have full QSK, but instead operates in a semi-break-in fashion, where the receiver is active between words and sometimes letters, but not between the dits within a letter. Well, that's it. Hopefully you found something of interest here, and if I've been lucky enough to have had a QSO with you, thank you for your patience. I hope you have as much fun with your next project as I have had with this one, and good luck.